2026 is here, and the hype around embodied AI is at an all-time high. But as we shift from research labs to the real world, the question is, what's actually ready for deployment? Today, we're cutting through the noise to find the signal in the silicon. Welcome to the state of embodied AI. Let's break down what's real, what's hype, and what's coming next.
Today, an artificial intelligence can pass the bar exam in seconds, diagnose rare diseases, and write college-level software. But if you ask that same trillion-parameter brain to pick up a coffee mug, it usually ends up smashing it. Despite recent breakthroughs, intelligence remains trapped behind glass screens. It operates in a purely digital realm, disconnected from the physical economy where the majority of real-world labor occurs. We already have industrial robots, but they are effectively blind. Traditional automation is deterministic, programmed to follow exact, rigid coordinates. If a part on the assembly line is off by a single inch, the robot doesn't adjust. It simply welds empty air. Embodied AI is a different approach. It refers to a closed-loop system of perception, reasoning, and action. It's a machine that senses its surroundings and adapts its movements in real time. True automation requires a mind that understands space and physical consequences. This marks the transition from tools that follow a script to agents that can navigate the world. Moving a physical body is exponentially harder than generating digital text. Every action is plagued by invisible variables: gravity, unpredictable friction, sensor noise, and mechanical wear and tear. A language model can learn by reading billions of documents in months, but a physical robot is limited by time and the laws of physics. Training a machine to move through trial and error is a painfully slow process. Because solving real-world physics is so difficult, progress has been slow. In the tech industry, that lack of progress often invites deceptive marketing to fill the gap. You have likely seen viral videos of humanoid robots smoothly folding laundry or brewing coffee. In many cases, these aren't autonomous. This is robot washing, where a human is remote controlling the machine using a tracking suit to simulate intelligence. To reach true autonomy, robots need millions of hours of trial and error training to learn how to handle objects independently. But collecting that data in the physical world is prohibitively slow and expensive. It's also dangerous. A robot making random mistakes during training can easily destroy itself or injure its operators. Since physical learning cannot scale, developers have been forced to move the robot's training into entirely virtual worlds. This is the sim-to-real problem. A robot might learn to pick up a box in a clean simulator, but fails in the unpredictable real world. Engineers solve this through domain randomization. They break the simulation by scrambling physical variables, altering gravity, lighting, and surface friction. By forcing the AI to succeed across thousands of chaotic variations, it learns to ignore visual noise and understand the core mechanics of the task. Creating an intentionally chaotic simulation is the only way to harden a digital brain against the unpredictability of reality. To move beyond simple motor skills, robots need a brain that can understand human intent. This is the role of Vision Language Action, or VLA models. This chart from Google DeepMind details their RT2 model. It treats physical commands like a language, predicting movement tokens based on what its camera sensors see in the environment. Further down, we can see the Pi0 model from Physical Intelligence. Instead of robotic, discrete steps, it uses flow matching to generate continuous, human-like motion, leading to significant performance gains in head-to-head tests. Because these models are trained on the entire internet, they already know what objects look like. This allows for zero-shot generalization, meaning a robot can follow a command for an object it has never physically seen before. These models allow the machine to reason about physical space, turning a high-level human intent into a precise physical consequence. Looking at the 2026 landscape, Tesla's Optimus program is a primary leader. They have a massive advantage in manufacturing scale and can test their robots in their own captive factories. At the same time, companies like Figure AI are deploying their humanoids in automotive plants to generate the massive real-world datasets needed to harden their software. But the entire revolution relies on a massive hidden bottleneck. Every one of these robotic brains depends on specialized compute infrastructure provided by NVIDIA and the chip fabrication capacity of TSMC. The winner of the robotics race won't just be the company with the best algorithms, it will be the one that commands the hardware supply chain. We should cut through the science fiction narrative here. Affordable robot butlers for the home are still years away from reality. In the immediate 2026 to 2027 window, current deployments are expensive pilot programs. They are focused on specific, dangerous, or repetitive industrial logistics tasks. The roadmap to 2030 relies on manufacturing scale to drive costs down to a target sub-$20,000 threshold. That is the price point required for mass adoption. Artificial intelligence is leaving the chat interface. The algorithms have learned to see and speak.
We've covered a lot, from the reality of foundation models like RT2 to the honest timeline for commercial scale. If you found this technical breakdown helpful, hit the like button and subscribe for more signal over hype.